Hi everyone, thank you for joining me today. This lesson will be on work and energy. This is lesson 2 in our series, and I will focus today mostly on, well, anything new today is going to be calculus based. So the first problem is a warm-up problem based off of last lecture, which I'd like everybody to give a shot on their own. And then we're going to get into looking at the more general forms of work and the work kinetic energy theorem, which would be calculus based. All right, so let's get started with our warm-up problem. A block is dragged along as shown. So we see that it's moving a distance of 15 meters. That's given in the diagram. We want to find the work done by tension, the work done by the normal force, the work done by friction, and the net work of the system. If you take a look at this diagram, you'll notice that there's actually a lot of information given. So let me just point some of those things out. First of all, the weight force is given. It's negative 30 newtons, which means we can quite easily find the mass, which you might need. The force tension is given. It's 25 newtons, and that's a two-dimensional force, right? It's at an angle of 30 degrees, which is important because you'll need to break it up into its components. And we're also given that the coefficient of kinetic friction, mu, is 0.21. And like I mentioned before, it moves a distance of 15 meters. So if friction's pointing to the left, that means the displacement would be 15 meters to the right. All right, pause here and give this a shot. All right, I'm going to go ahead and just draw out my free body diagram on my paper and also list up my knowns. So my knowns may not have been explicitly given in the word problem, but there was a lot in the diagram that I could figure out. For example, my mass would have been my weight force, which was negative 30, divided by the acceleration due to gravity, negative 9.81. So my mass is 3.1 kilograms. My displacement was shown as well. It's 15 meters. And then I have my coefficient kinetic friction is 0.21. And my force tension is 25 newtons. So I have my force tension here at some angle theta, which was 30 degrees. I had my gravitational force pulling down, my normal force pushing up, and then friction opposing the motion. My first question here is to find the work done by tension. Now, the work done by tension is going to be equal to the x component of tension times the displacement. Right? I mean, I can actually use that equation, which was Ft times delta x times cosine of theta. That is the same thing as this, right? If this is my force tension, then my x component is Ft cosine of theta, and my y component would be Ft sine of theta. That's theta. All right, so I have 25, right? My force tension is 25 times the cosine of 30 times my displacement of 15. That gives me 325. 25 cosine 30 times 15 is 325 joules. That's the work done by tension. Next, I'm asked to find the work done by the normal force. Now, the normal force is completely perpendicular to my displacement, my delta x, which means that there's actually no part of this force contributing to this energy transfer at all. So the work done by the normal force is 0 joules. Right? I mean, you could plug into our general equation if we wanted. We could say the work done by the normal force would equal the normal force times the cosine of angle theta, but the cosine of 90 degrees is 0. So multiplying the normal force by 0 is going to give us a 0 anyways, right? Okay, very good. So the next part is finding the work done by friction. And as I look here at my free body diagram, my information, I don't actually have my force friction. So I need to figure out what that value for my force of friction is first, which I can do using this relationship, right? My force friction is equal to mu times the normal force. So I should find my normal force. My normal force is in the y direction. So I should sum together my forces in the y. I have normal plus the y component of tension. Whoa, I wrote Fy. I didn't mean to write that. I should have wrote Fn. So my normal force plus my force tension, the y, plus my force gravity. And that equals MAY. And the acceleration in the y direction is 0 here because this object is being displaced horizontally. There's no vertical displacement. So the acceleration of the y is 0, or the vertical acceleration is 0. So using this equation, I can I can isolate Fn in MAY minus FTY minus FG. And I get 0, right? That's my mass times 0, minus FTY is 25 times the sine of 30. Minus my force gravity was given, or my weight force was given on the diagram as negative 30 newtons. So I have 30 minus 25 sine of 30 is 17.5. So my normal force is 17.5 newtons, which means the work done by normal is equal to my normal force multiplied by the displacement. Right? My normal force, oh, sorry, that's not what I'm looking for. Silly me. I'm looking for my force friction, which is equal to mu times my normal. So my force friction is going to be equal to 0.21 times 17.5. So 3.7 or 3.68. My pen's struggling here. Now, this solved for the magnitude, right? You can see there's no vector notation here because this relationship is a ratio, right? Mu is a ratio of the absolute value. So anyways, I don't actually know the direction yet. So let me just look back at my free body diagram. It's pointed left. So this is a negative 3.68 newtons. So the work done by friction is going to be equal to the force of friction times the displacement. And friction is entirely parallel to my displacement. So I'm going to use my entire negative 3.68 times my displacement was 15 is 55.1, or negative actually 55 joules, right? It's negative. So there was 55 joules of energy lost due to friction. So the net work is going to be the work done by each of these forces. So the work done by friction, the work done by friction plus the work done by normal plus the work done by tension plus the work done by gravity. So my work done by friction is negative 55. The work done by normal is 0. The work done by tension was 325. And the work done by gravity is 0, which we didn't explicitly state yet. But because the entire force of gravity is perpendicular to the displacement, gravity is not contributing at all to that energy transfer. So that's also 0 joules. So we have 325 minus 55, and that's 270 joules. That is my net work. All right, good work with this problem. So we understand now how to calculate the work done on an object when the force is constant. But what about if there's a variable force? There are actually a lot of examples of variable forces in real life, like the spring force, for example, is a common one. If you imagine stretching or compressing a spring, you may remember, if you've ever done something like this, or even a rubber band or anything that's sort of elastic, the force often gets way more difficult to stretch as you pull it farther and farther apart. The force varies based on the displacement from the resting position. Sometimes it's easy to pull it first and then not really so much. So how would we calculate the work done when the force changes with position? And this is where calculus comes in. So instead of treating the entire motion as one big interval, we imagine that it's broken into thousands of tiny parts. So really actually infinitely many tiny parts, which is of course what you know to be integration. So over one tiny distance, which we can call dx, the force doesn't change very much, right? If you imagine taking the distance of something being stretched, right, and making that infinitely close to zero, but not quite zero yet, well, the force isn't changing very much. So for that tiny interval, we can pretend that that force is constant, which means that the tiny amount of work done over that small distance is approximately equal to this here. So each little piece contributes to a tiny amount of work done. And then to find the total work, we would simply add all of these tiny pieces together, which is what integration is. So our formula for work becomes here, this right here, what I circled in black. Now, instead of multiplying one force by one distance, we're adding up all the tiny amounts of work as that force changes from the starting position, xi, to that final position, xf. And you could think of this visually, right? If you were to graph, for instance, the force versus position, the work done is simply the area under the curve. So for a constant force, the graph would be a rectangle, and integrating a rectangle would be multiplying the force times the displacement, right? Which is what we know to be the work formula up until right now when we're learning this more general formula. So this new, well, not new, I put air quotes around that, this new equation for work is just a general form of work. It's not necessarily a new equation at all. It's just one that works for all cases, not just with constant forces. So try this problem then. A particle experiences a force given by f of x equals 8x plus 9, where f is measured in newtons and x in meters. Determine the work done as the particle moves from x equals 0 meters to x equals 2 meters. So for this next problem, we have a variable force, which means we should be using our calculus. So we just learned that the work done on an object is equal to the integral between the initial x location and the final x location of the force as a function of x. So what we'll do to find the work here is we'll take the integral from 0 to 2 meters of 8x plus 9 with respect to x. Now, to integrate this function here, we're going to add one exponent onto the current exponent for x. So we're going to make that x to the power of 1, x to the power of 2, and then we will divide by that value 2, the new exponent. And we'll do the same over here. So we have 8, the integral of 8x becomes 4x squared, right? Because I added 1 to make that 2 and divided 8 by 2. Now, this 9 has a value next to it of x to the power of 0, which is just 1. So I got to add 1 onto that 0 exponent and make that 9x, and then I'm going to divide that 9 by 1. So I have 9x. And this is a definite integral from 0 to 2. So what I'm going to do is I am going to plug in my 2, and then from that subtract. So take this new function, plug in 2 for x, and then subtract this function with 0 in it, which would be 0. So I have 4 times 2 squared plus 9 times 2 minus 4 times 0 squared plus 9 times 0. So 2 squared is 4 times 4 is 16, plus 9 squared is 18. Oh, sorry, plus 2 times 9 is 18, minus 0 plus 0 would give us 24. Yeah, this is wrong, right? 34 joules. Now, just like we use calculus to get the general form of the work equation, we can do the same for the work kinetic energy theorem. This theorem states that the net work done on an object is equal to the object's change in kinetic energy. So if we know that the net work, right, we learned right here that the work is equal to the integral of f of x with respect to x, then it must also be true, if the net work is equal to the change in kinetic energy, that the change in kinetic energy would be equal to the integral of the net force of x with respect to x. And if change in kinetic energy is Ke final minus Ke initial, then this equation can also be expanded to look like this. So you can see here that we can use this relationship to solve for the speed, even if the force is changing throughout the situation, which can be very useful. So try this problem here. A 12-kilogram cart starts from rest. The net force acting on it varies with position according to this function, f of x equals 2x plus 10. Determine the cart's speed after it has traveled 5 meters. All right, so for this problem, I will need to use the work kinetic energy theorem, that work is equal to the change in kinetic energy, and that equals the integral of f of x with respect to x. So let me figure out first what the change in kinetic energy is. And for this specific case, we have after it's traveled 5 meters, so we'll say maybe from 0 to 5. You get the same answer if you went from like 10 to 15 or 20 to 25 or 32 to 37, as long as the difference between these two values is 5. Anyways, we have the function 2x plus 10. We got to take that with respect, integrate that with respect to x. So first we take this x1 at 1, we add a value to it. So we add 1 to it, we get 2, and divide it by 2. So we get x squared plus, and this, we add an x onto this guy as well, so plus 10x. And we will find the solution for between 0 and 5 meters. So we have 5 squared plus 10 times 5 minus 0 squared plus 10 times 0. So this is going to be 25 plus 50 minus 0, or 75 joules. That's my change in kinetic energy. Now the problem's asking me to find the cart's speed. So I will need to think about what the change in kinetic energy is, right? And that is the final kinetic energy minus the initial kinetic energy. Now, the kinetic energy equation is 1/2 mv squared. So this delta Ke can be expanded to be this relationship here. And I'm told that the cart starts from rest, which is really important because this whole term goes to 0. So I'm looking for my V final. I know my mass, right? My mass was 12 kilograms. I know my change in kinetic energy. That was 75 joules. So this is what I need in order to solve for my speed V right here. So if I want to take this equation and isolate V, the first thing I want to do is get rid of this 1/2, which I can do by multiplying everything by 2. And I get 2 times the change in kinetic energy equals mv final squared. And again, I'm trying to isolate V final, so I can get rid of this coefficient by dividing everything by m. And I get 2 times the change in kinetic energy over m equals V squared. And last thing I can do to get V alone, well, it's really V final, is take the square root of everything. So the square root of 2 times the change in kinetic energy over m equals V. And now I'll plug in 2 times 75 divided by 12. So 150 over 12. Take the square root of that. And that gives me my speed, 3.5 meters per second. Thank you guys so much for tuning in today, and I will see you soon with our last lesson on work and energy.